In the last video, we were able to determine the current flow through the total load from the power supply. So this is where we now start. One known current, I1, which is equal to 3 amps, and the known power supply voltage, which is 460 volts. Using Ohm's law, the voltage drop across R1 is equal to I times R, or 3 times 20 for 60 volts. Because the current must split equally into 3 identical resistors, which is Kirchhoff's current law, I4 must equal I3 must equal I2 must equal 1/3 times 3, or 1 amp. Again, using Ohm's law, the voltage drop across R2 is 1 times 100, which is equal to 100 volts, which also equals the voltage drop across R3 and R4. The voltage drop from C to F can be calculated, which is the supply voltage E minus the voltage drop AB plus BC, or 460 minus the quantity 60 plus 100, which is equal to 300 volts. A current will now flow from C to G to F, splitting, of course, as it flows through the parallel resistor combinations. We already know the parallel resistance of C to G is 300 ohms, and we already know the parallel resistance G to F is 300 ohms. Therefore, the total resistance C to F is 600 ohms. Again, using Ohm's law, the current C to F is 300 volts divided by 600 ohms, or 0.5 amps. Since we know that VCF is 300 volts and the resistance from C to F is made up of 300 ohms C to G and 300 ohms G to F, then the voltage will be split in half, 150 volts C to G and 150 volts G to F. That means the voltage drop across R5, R6, and R9 is equal to 150 volts. We can now use Ohm's law to calculate the current through these resistors. I, R9, is equal to 150 divided by 600, or 0.25 amps. I, R5, is equal to 150 divided by 1000, or 0.15 amps. And I, R6, is equal to 150 divided by 1500, or 0.1 amp. The total of IR5 and IR6 currents is 0.25 amps, which means the current through R7 and R8 is equal to 0.5 minus 0.25, or 0.25 amps. We can now use Ohm's law to calculate the voltage drop across these resistors. V, R7, is equal to 0.25 times 200, or 50 volts. V, R8, is equal to 0.25 times 400, which is equal to 100 volts. Using the same logic, we can calculate the current through and the voltage drops across R10 and R11. Using voltage division, we know that IR10 and 11 equals 0.25 amps, and the voltage drop across R10 is equal to 0.2. The voltage drop across R10 is equal to 0.25 times 400, which is equal to 100 volts, and the voltage drop across R11 is 0.25 times 200, which is equal to 50 volts. Kirchhoff's current law states that the algebraic sum of currents entering any node or junction of a circuit is equal to the algebraic sum of the currents leaving that node or junction. Applying Kirchhoff's current law at node C, we find that the current entering, 3 amps, minus the current flowing down, 0.5 amps, must equal the current in R12, which is equal to 2.5 amps. Therefore, using Ohm's law, the voltage drop across resistor R12 must equal the current through R12 times the voltage drop of R12, or 2.5 times 20, which is equal to 50 volts. And that current 2.5 amps flows all the way to F, splitting at node D, but converging to 2.5 amps at E, splitting again at node D, but converging to 2.5 amps at F. Remember, this is a simplified circuit, and the current through branch CDEF is 2.5 amps, and the voltage drop from D to E, according to Ohm's law, is 48 times 2.5, or 120 volts. Therefore, the voltage drops VR 15, 16, and 17 are also 120 volts. This means, according to voltage division, VR13 is equal to 100 volts and VR14 is equal to 20 volts. The current in R15 and R16 and R17 can now be calculated using Ohm's law or current division. The current through R15 is 120 divided by 100, or 1.2 amps. The current through R16 is 120 divided by 200, or 0.6 amps. And the current through R17 is 120 divided by 600, or 0.2 amps. These currents add to 2.0 amps, which means since the current through CDEF is equal to 2.5 amps, then according to Kirchhoff's current law, the rest of the current, 0.5 amps, must flow through R13. And R14, the current flowing from E to F, is 2.5 amps, and because R18 and R19 are equal, the current of 2.5 amps will split evenly, such that the current through R18 is 1.25 amps, and the current through R19 is also 1.25 amps. The last thing we need to calculate is the voltage drop across resistors 18 and 19. For that, again, we will use Ohm's law. The voltage drop across R18 is equal to a 1.25 times 104, or 130 volts, and VR19 also equals 1.25 times 104 for the same 130 volts. We have successfully computed the current through and the voltage drop across each resistor in this circuit. Any circuit with a single power source can be reduced to one equivalent resistance, no matter how complex, and can be solved in a manner similar to the preceding procedure. This, by the way, is also known as Thevenin's theorem. Before closing, I want to let you in on an early Prime Day sale at 𝐃𝐈𝐒𝐂𝐋𝐀 Canada solar generators. Simply go to this web address, which will allow you to get in on up to 65% savings. This brings us to the close of this section of the problem and its solution. If you want the full range of problems and their solutions, you can find them by going to my Stan Store at this web address. And finally, my newest course that I just added, Bridging the Gap Between Theory and the Practical. This course was developed specifically to solve the pain point of those newly introduced to the power industry. Whether you're an engineer, technologist, or electrician, this course is designed to give you a preview of what's ahead of those just leaving the halls of book learning and entering into the electrical power industry.